I'm here today to talk about a system that we've built called Pequod. But before I begin, I'd like to mention that this is a collaborative effort with my colleagues both at Harvard and at MIT. In this talk, I hope to convince you that application caches should include native support for materialized views. And further, I hope to show that web applications built within cache view materialization both have good performance and are easy to program. This talk is about web application caches. And if you don't know, an application cache is a fast key-value cache that's deployed in a data center alongside your other web architecture components like a web server and a database. And there are many such examples. For example, Memcached and Redis are very popular. And the reason you might deploy an application cache is to absorb reads that would otherwise be forwarded to a database. Now, application caches are completely managed by the developer. This gives them the freedom to store arbitrary data for fast retrieval, but this also makes them assume the burden of cache maintenance. They need to keep the cache fresh. So throughout the talk, I'll use an example application of Twitter. We'll show that Pequod could help Twitter's developers, but of course the abstraction applies to other web applications. So at its core, Twitter allows users to talk to each other. And a Twitter user who loads the service in his browser might see this, which is his timeline. It shows a list of things that other people have recently said, but the timeline actually represents the result of some computation. It's derived by joining two pieces of base data, specifically the user's subscription list and the post of other users, and then the result of the join is filtered and sorted before it's being returned to the user. So this is a fair amount of work, actually, to construct a single timeline. And what's worse, timeline checks are actually very frequent. They're about 100 times as frequent as new posts in the actual Twitter service. So with this kind of heavy read workload, the application developer may resort to an old trick, namely caching. So here we have a Twitter developer, and they've deployed an application cache to help serve user timelines. And since the cache is under her control, she gets to decide what to put into the cache. So what should she put into the cache? Well, a good start would be to put the thing that she wants to read out, at least in the most convenient form, which is fully constructed user timelines. And as of 2012, this is precisely what the developers at Twitter actually implemented, and they use Redis. So if the cache contains ready-to-read timelines, then timeline checks should be really easy. The application simply asks for the user's timeline, and assuming a cache hit, they construct a response to the user. This is a very simple interaction. But for the cache timelines to be useful, they must be kept fresh. And as a result, for every new post that enters the system, it's both persistent in the database and it's used to update the application cache. Now, the user that posted may have hundreds, thousands, or even millions of followers, each of which may have a cache timeline. So performing these updates is not a problem, but deciding which cache entries to update, that is, which followers have cache timelines, that is a challenging problem. It adds unwanted complexity to the application, and it causes undue harm to the developer. So naturally, the developer might be looking for a simpler solution, and she might turn her attention to the database. Database researchers have been simplifying data access for decades, and this SQL query fetches the posts in a user BK's timeline since the time 100. So it's deceptively simple here. It's only 6 lines long, but SQL, as it's designed to do, hides the complexity of this query, which involves a fair bit of computation, joining, projection, filtering, sorting, to produce this result. So if we're to run this query for every timeline check, the database would quickly become a bottleneck. There are far too many timeline checks to be computing an expensive join for each one. So fortunately, database researchers realized that this was a problem, and they provide another solution, materialized views. A materialized view is a database query whose results are stored into a table. The table is then kept up to date as the inputs are changed. So these SQL statements use materialized views. They produce results that are identical to the previous query. However, the materialized view approach uses a very different execution strategy. The T-line table stores the pre-computed timelines for all users, and the table is then kept up to date as users modify their subscription lists and make new posts. Now, compared to the previous query, retrieving a user's timeline involves very little on-demand computation. The materialized view shifts the computation to the right path, and it has the added benefit of simplicity. So this is really good, but how does it perform? Not so well. While the materialized view definition is extremely simple, and its execution strategy puts the computation in the right place, it's just not enough to prevent the database from becoming a bottleneck. The database is deployed into our architecture for a reason. We want to persist application data. So it shouldn't really be expected to handle that write workload along with the tremendous amount of reads generated by timeline checks. We must cache cache application data for good performance. So where does this leave us then? We're kind of stuck. Well, ideally, we'd like to have a system that combines the performance benefits of a key value application cache with the ease of use of materialized views. Pequod is that system. So Pequod, our system, is a distributed application cache that features materialized views. But these aren't your mother's database materialized views. They need to execute in the context of a key value cache, which has an admittedly narrower interface. Pequod supports the familiar get and put operations along with an ordered range scan and a new join operation which installs a materialized view into the cache. Thanks to materialization, applications built with Pequod both perform well and are much easier to program. Now, the distributed key value context presents some challenges to implementing materialized views in the cache. Pequod borrows several advanced materialized view features from recent database research in order to make this work. So views in Pequod are materialized partially and dynamically, and then the views are maintained incrementally using both eager and lazy maintenance strategies. This combination of features seems new to caches. Database materialized views, they depend on the relational model, arbitrary columns and projection, but Pequod doesn't have a relational model. It has a key value model. It only supports get, put, and scan. So how does Pequod represent relations? Well, we do it by decomposing the keys into columns. This is the syntax for the same timeline materialized view. We call it a Pequod cache join. This cache join defines a range of derived keys, those with the prefix tline, that's analogous to the tline table from the SQL definition above. Now here I've labeled the parts of the join definition, and I've highlighted the cache keys in blue. The join defines how output keys, that's the tline, user, time, poster, are calculated from the other keys and values in the cache. There are two things to note. First, that columns are now stuffed into these keys, and second is that the values are handled differently. In this case, the copy operator indicates that the post value is copied into the timeline. Now, the order of the columns is in the key is important here, and this is because of the scan operation, how we're actually going to access the data. So given this cache join, here's a version of the timeline request from earlier, but now it's implemented in Pequod as a range scan. This returns BK's timeline starting at time 100. The timeline scan executes over one user's timeline for a range of times. Thus, the user and time components appear in the tline key format in that order. Okay, so let's see how this works. Initially, Pequod's loaded with base data, the subscription lists and posts of users, or it at least knows how to get them. The timeline range, which is defined as the output of the cache join, is empty until it's queried. So when a query arrives, Pequod notices that the request range is empty, and it checks to see, is there a join that I can use to create some data? There is, and Pequod executes it, which creates the timeline, caches it, and then returns it to the application client. But Pequod also remembers the base ranges that were used as inputs to this timeline for the purposes of future incremental updates. For example, when Mike later posts, Pequod automatically copies that post into BK's timeline. This is eager incremental view maintenance. It's good because later reads of BK's timeline will require no computation. Now, Pequod's very flexible, and it supports other forms of view maintenance. For example, if BK subscribes to a new user, Neha, the timeline range is updated lazily. That is updated on the next query. For application developer, they have control over these types of policies, and there are other policies that are mentioned in the paper. Pequod can be deployed as a distributed system. The key design choice we made was to make all computation local. This means that every query is computed on exactly one server. We scale by computing different queries on different servers in parallel. When a query executes, all of the input data that it needs must be resident in one server's memory. However, the system as a whole is able to handle data too large for any one server. To do this, base data such as the subscription list and posts are partitioned amongst the servers using an application-defined partitioning function. The query can be executed on any server, and the input data that is not resident on that server when the query starts is then transparently replicated to the server before it begins. This has, of course, some limitations. For example, base data can be replicated on many servers, which may reduce scalability. But as I'll show you, the system scales well. So let's just see an example of this. Here we have a distributed Pequod deployment with the base data partitioned by user. If a timeline request for user BK is received at the first server, it'll attempt to execute the timeline cache join. However, that data that it needs is actually spread across all these other servers. Pequod transparently requests the data, and in this case, the posts of Eddie and Mike, and it gets them from the other servers. The other servers will respond with the data requested, and they'll record metadata that indicates the first server is now subscribed to these data ranges. The replicated data is cached on the first server and used to compute BK's timeline, which is eventually returned to the client. So if user Mike posts in the future, that the post may say is written to a database, Pequod might observe it, and the server that's responsible for Mike's post will use its subscription metadata that it recorded before to forward a copy to the first server, where it's then eagerly propagated into BK's timeline as before. So I want to note also on this slide that this demonstrates one way in which we expect Pequod to be deployed as a write-around cache. The application would send reads to the cache and writes to the database, and then Pequod would snoop on the database writes to update its own base tables accordingly. Now, we've implemented this model, and we've also implemented a more direct model where the application writes both to the database and to the cache. So Pequod supports other more advanced features I don't have time to discuss in depth, but I will mention a few of them here. So cache joins, which are very flexible. They're flexible thanks to the key value model, and they support advanced features that are useful for some applications and not for others. For example, multiple cache joins can output to the same range of keys. This might be helpful to an application because it brings different kinds of data together for easy access. Now, the output of one cache join can be used as the input to another, allowing them to be stacked together. Cache joins are materialized by default, as I mentioned before, but they can also be marked as non-materialized to save memory, and Pequod can also save snapshots of materialized ranges that will automatically expire after some time. Now, Twitter uses that copy operator in its join, but Pequod also supports other operators, aggregate functions such as count, that will count the keys in a given range. And as a cache, Pequod, of course, can evict data under memory pressure. We also evict dependent data as is necessary. And finally, I want to have a word on consistency. That word is eventual. We discuss consistency more in the paper. So now that we sort of understand how cache joins work, how well do they perform? I'll share with you the results of two experiments, both of which use a Twitter benchmark that includes timeline checks, subscriptions, and new posts. In this experiment, we want to evaluate the performance of Pequod itself, and so we omit the database. The first experiment compares Pequod to other systems. Now, specifically, we want to know if cache joins have similar performance to standard key value cache. Our goal isn't necessarily to outperform these other caches, but to do no worse. Now, since Pequod offers improved programmability, this would still be a win for us. In this experiment, we compare Pequod with two popular caches, Redis and Memcached, and neither of those systems has built-in materialized view support, so those applications manage the cache manually. We also compare Pequod with another system that does support materialized views, namely a relational database that runs in memory as a cache. We chose Postgres and simulated the materialized views using table triggers. So each system was given 6 cores on a multi-core machine, and the Twitter benchmark was executed as fast as possible. So here are the results. We're showing here the average query throughput over the entire benchmark run, and larger bars are better. Now, as we can see, Pequod does accomplish its goal, performing no worse than the other key value caches. In fact, it performs a little bit better for this workload. And the reason for that performance is cache joins. Redis is a dumb cache, so a new post in that system turns into many RPCs on the cache. Pequod, on the other hand, handles a new post with a single RPC. Now, a version of Pequod that ran without cache joins actually performed worse than Redis. And so we can see that it can be advantageous even for performance to move computation into the cache. The comparisons with Memcached and Postgres are not particularly fair. This workload has many more puts than Memcached prefers, and although Postgres was tuned and used as an in-memory cache, we disabled many expensive features. It really was designed as a persistent store. And since it's not designed as a cache, its performance is not that surprising. In the second experiment, we explore the scalability of Pequod's design. So what we want to know is there an advantage to adding servers to a Pequod deployment that's experiencing heavy load? And if so, what is the overhead associated with scaling? Now, to answer this question, we deploy Pequod in a 2-tier fashion on Amazon EC2. The set of base servers stores the posts and subscription lists, and the second set of servers, we'll call compute servers, will compute all the timeline cache joins. The compute server pool was expanded from 12 to 48 over the course of the experiment, and these are the results. We can see here an increase in the number of compute servers from 12 to 48 results in a significant but imperfect 3x improvement in system-wide throughput. Perfect, of course, would be 4x. This is actually an encouraging result. I mean, it's showing that the Pequod can scale a deployment to add computational capacity to improve application performance. What about that overhead? Scaling is imperfect because the overhead's associated with data movement among these cache nodes, that is, between the base and compute servers. For instance, consider a popular user listed in many other user subscriptions. A tweet by that user will end up replicated on many of the other compute nodes, maybe even all of them. This takes up both network bandwidth and memory. Now, the bandwidth required to propagate data between the base and compute servers did indeed increase in our experiment with the number of compute servers, but it was still relatively low. The total memory consumed by all Pequod servers did increase as well, even though the experiment stayed the same. So this is a consequence of more data replication and more subscription management as the number of servers increases. So overall, this overhead is noticeable, but it doesn't appear to be a critical barrier to scalability, at least up to 48 nodes. And we stopped the experiment at 48 nodes because after this, the bottleneck shifted away from Pequod. So as I mentioned, Pequod uses advanced materialization techniques from recent literature to implement these cache joins. And I'll list only a few here. There's more related work, of course, in the paper. And the concepts behind partial materialization that we use and dynamic view selection were described in a Microsoft research paper by Zhu et al. They implemented dynamic materialization in the SQL Server. DB proxy is a distributed cache that uses edge nodes to absorb reads. These edge nodes are actually databases themselves. This work uses incremental maintenance for cache upkeep, just like we do, but they actually preserve the relational model. This has some advantages and disadvantages, as we've seen. And finally, the materialized views, these were added to Peanuts, which is a distributed key value store. Like Pequod, the system uses data replication to materialize join views. However, it does not support partial materialization or the key-based computations that we designed using our ordered key value store. So in conclusion, excuse me, I hope that I've been able to convince you that materialized view abstraction is a useful one, and that key value caches should offer this abstraction to their developers, even if it's just for the sake of their sanity. Thank you.
Questions?
Really great talk. It's good to see a database talk at NSDI.
If you can call it that.
Wondering about a couple of things. First of all, you talk about queries per second, but what about latency? There's obviously overhead in constructing these materialized views, and it's really critical. Twitter in particular, users expect low latency response. So that's one issue. Another is you talked about eviction, but what really happens under memory pressure? I would think that this could lead to a lot of reconstructing of materialized views. And thirdly, what about the currency of the data? So you talk about comparing to Redis, but with materialized views, there's updating. There's likely to be a lag, so you're not always necessarily seeing the most up-to-date data. And again, in the case of Twitter, people expect not only low latency, but the most immediate results. So, can you comment on this?
Sure. The first part was about latency. I don't have any specific numbers to quote to you, but you're right that you might see a latency spike, for example, on the first time a cache join is computed, especially if that data is not a cache resident. This is really a sort of a cold cache problem. At least what the Twitter engineers did was have a cache that's large enough to hold 2 weeks worth of recent data for every user who's logged in the last month. So they solved that problem by just scaling out. We could do something similar. The second question was about... Wait, what's the first question was about?
You're expecting me to remember my own question?
So the first question was about latency. So the point of the pre-computing, the materialization, is to have those timelines ready to read. And so theoretically, if you have enough room to keep them all, that's a very low latency operation. Second was memory pressure. Thank you. In the paper, we do a very simple form of eviction. We will evict whole computed ranges at once. In my PhD thesis, I'm working on some more advanced techniques to evict partial ranges and to have different policies that say evict computed data versus base data, knowing what the degree of dependencies are on that base data. And the third was recency. Currency. Web application developers have grown accustomed to eventually consistent systems, especially in caching. I know that at least in the real Twitter system, they use this type of deployment, and writes do trickle through their system. They say it takes. They say they want it to take under a few seconds, and in general, it takes less than a second for a new tweet to trickle out to all the users. So I think that's just something they have to put up with. Maybe you can use some other tricks to make sure, for example, that the poster sees their own tweet, but the followers, they'll get it when they get it.
Okay, I just think for the purpose of comparison, it would be good to have that in your results.
Thank you.
Should probably. I think you've got time for one more question. Hopefully, a slightly shorter question.
Thank you.
The question was optimized for sort of throughput, not latency, I think.
I am optimized for latency from DynamoDB.
Excellent.
So this is really cool stuff. By the way, I see two problems here. One is, this is really cool, but one is transparency of the business logic. You're putting a lot of business logic on the cache layers, and the composability. Like the moment people start to nest things through materialized views, latency goes way higher. And how does the developer know where this latency bottleneck is?
Yeah, so we've taken a lot of what you would normally put into a database schema, and we sort of squished them into keys. So that's definitely a problem once your application grows more complex. In terms of stacked cache joins, all that updating mechanism happens on the write path, not on the read path. So it probably wouldn't cause latency spikes for reads. However, if you had to generate something that's the third generation cache join from scratch, that would certainly generate a large latency spike.
Thank you.
Okay, thanks very much.